have a nodding acquaintance with the major planets in our solar system. But there are a host of other objects to be found.
Many people think of the major planets in the solar system as the most glamorous components of this part of space. But actually, the so-called minor members of the solar system, including things like these meteorites, are every bit as enigmatic and exotic as the major planets. The minor members of the solar system include the comets, whose orbits can extend far beyond the orbit of the planet Pluto, and in, of course, close to the sun, so that sometimes when comets get into the solar vicinity, they appear to develop long tails and huge heads, which we see decorate our nighttime skies. And the minor planets, planet-like objects whose orbits, for the most part at least, are restricted to that area, that zone between Mars and Jupiter. We also find in interplanetary space meteoroids, really rocks in space that are also traveling in orbits around the sun. And occasionally, one of these may intercept and strike the Earth to be picked at hand. There's also interplanetary dust and interplanetary gas out there, and it almost seems as though we're filling up the spaces between the planets with these minor members. But actually, a sample of that interplanetary space, at least in the neighborhood of the Earth, is a much better vacuum than we can produce here on the Earth's surface.
Between the orbits of Mars and Jupiter, in a region called the asteroid belt, are the minor planets, sometimes called asteroids. Over 2,000 of the larger minor planets, ranging in size from about a mile to 500 miles in diameter, have been named and have had their orbits calculated. But tens of thousands of smaller asteroids have been observed. When a telescope is used to photograph the asteroids, a clockwork mechanism allows the telescope to follow the stars across the sky. On photographs made by exposing the film for several hours, the stars produce bright, round images, while the asteroids produce elongated images or trails. This is the photographic trail produced by Eros, a minor planet which sometimes passes as close as 15 million miles to Earth. Most of the asteroids stay close to the same plane along which the planets move. There is no universally accepted explanation for the formation of the minor planets between the orbits of Mars and Jupiter. Possibly Jupiter's strong gravitational force somehow prevented a single planet from forming there.
There are two ways to think of dividing up the minor physical properties. In terms of orbits, most of them have orbits of moderate eccentricity and ellipticity between that of Mars and Jupiter. This is the so-called asteroid belt. In addition, there are a few peculiar objects. There are some whose orbits are more elliptical and which cross Mars and come in close to the Earth. A very few even cross the orbit of the Earth, and in a very few cases indeed, the orbit of Venus. These little objects, and they are no more than a few kilometers in diameter, that come close to the Earth are called Apollo asteroids or Amor asteroids, after their prototype members. There are, in addition, a few asteroids that go further out than the main belt. Those are called Trojans, that have positions at about the distance from the Sun of the orbit of Jupiter.
There are some indications that minor planets have undergone processes of differentiation and heating, which would imply that they must have been inside large bodies. And that raises the question, how did they get out? We don't know. One suggestion is that the minor planets are the remnants of a single planet that somehow exploded or simply broke apart, and that the dense metallic asteroids and meteorites came from the interior of that ill-fated planet. But of course, what's lacking is an acceptable explanation of how a planet could in fact explode or break apart.
Many of the meteorites show evidence of once having been a part of larger ites, must surely have been formed in iron cores of differentiated planets. We can't say, however, how large those planets were. Most of the kinds of tests that can be made on the meteorites suggest only that they were at least a few hundred kilometers in diameter. And that's still a lot smaller than we usually think of as a planet. So if these meteorites come from the asteroid belt, as seems the most probable origin for them. What we are really saying is that there once was a group of asteroids, at least a few hundred kilometers in diameter, that were heated and differentiated. I think this is what the meteorite parent bodies are. Many planets, but planets that were still large enough to go through this kind of evolution. Other meteorites, by the way, such as the carbonaceous chondrites, show no such evidence of heating. And it seems probable that the majority of the asteroids, which are also dark and carbonaceous, also escaped this kind of thermal evolution. So probably we have at least two kinds of asteroids: those that are still primitive material of the sort that condensed originally to form the solar nebula, and others that have gone through heating and differentiation. Most of the asteroids are very dark, some of the lowest reflective objects in the solar system. And we think that this darkness is due to the presence of fine grains of carbon and carbon compounds. In fact, these objects look a lot like the carbonaceous chondrite meteorites that fall to Earth occasionally. Other asteroids are lighter and red surface mineralogy that we associate with ordinary silicate rocks. A few of them are even more extraordinary. There's evidence that some of the asteroids may be metallic in surface composition, probably composed primarily of nickel and iron. And one asteroid, the second largest, Vesta, has a surface that has basalt, that is, lava rocks, which surely indicates that this object has gone through the same kind of interesting geological history with volcanoes on the surface or something similar to that we normally associate only with the larger planets. Shortly after astronomers could first measure the distances to the planets, they recognized that there appeared to be a sort of gap between Mars and Jupiter. And there was lots of speculation that maybe there was an undiscovered planet in this gap. In fact, toward the end of the 1700s, quite a few astronomers attempted to search, and in those days it was purely a visual search, for this missing planet. It was discovered on the first day of the 19th century. A monk in Sicily discovered a small stellar-looking object which moved from night to night. And it was possible to calculate, after a series of these observations had been made, that this little minor planet was indeed in the place between the orbits of Mars and Jupiter where it had been suspected such a planet should be. It was an awfully small planet, though, and the situation was further complicated a year later when another planet in approximately the same orbit was discovered. First was called Ceres, then came a whole series of little objects: Vesta, Juno, Pallas. And by late in the 19th century, hundreds and hundreds of these were being found. Objects with a maximum size of a few hundred kilometers, and many of them ever so much smaller.
Using a technique of photographic time exposures, scientists can identify light streaks or light signatures of both moving asteroids and man-made satellites. Eleanor Helene, a senior scientist at the California Institute of Technology, has conducted extensive studies of asteroids whose orbits cross the Earth's.
Perhaps the most unique discovery during our program has been the discovery of what is designated as 1976 AA, which is the first asteroid or minor planet that has ever been found. It has an orbit smaller than that of the Earth. In other words, a semi-major axis less than 1, a period of less than a year. It's totally unique in these characteristics. Also the fact that it's the first minor planet that does not cross the orbits of Mars or Venus. It is also the first asteroid on discovery in which we were able to get photometry and radiometry measurements, so we have some feel, some idea of the composition of the asteroid.
Sometimes pieces of the solar system fall to Earth, and we're able to pick them up and examine them. When these rocks from space strike the Earth, they're called meteorites, and there are one chance, really, to get a hold of material that comes from interplanetary space. Actually, there's some confusion over some of the terms that surround meteors and meteorites. A meteoroid is simply an object in space as it's traveling and orbiting around the sun, whether it be the size of a grain of sand or perhaps a huge rock or boulder. When one of these objects enters the Earth's atmosphere, It heats up the material, the gas in the Earth's atmosphere through compression, and we see a trail of fire, at least so it appears. That heated gas, that trail that we see, is the so-called meteor. And should one of these objects actually make it to the surface of the Earth without completely burning up, then that rock or piece of material which lands and is perhaps found later is known as a meteorite.
Well, we have three main kinds of meteorites. They are called stone, iron, and stony iron meteorites. The stone meteorites being principally made up of stony material with flecks of nickel iron dispersed throughout them or disseminated throughout them. The iron meteorites are principally composed of iron with typically 7, 8, 10, 12% nickel added to it. And then the stony iron meteorites are roughly equal percentages of nickel iron metal and stony material. The stone meteorites are the most abundant of all the meteorites, comprising about 95% of them. If we cut open a typical stone meteorite, we find the inside to be rather light in color. And if I tip this just right, you can see the flecks of nickel iron metal that we find in the meteorite. Because of those flecks of nickel iron metal, the meteorite is slightly magnetic. That is, it's slightly attracted to a good magnet. And the flecks of metal are pretty good criterion as to what we have here, because you're not going to find flecks of such metal in terrestrial rocks. At least very, very rarely is it ever found. Iron meteorites do not fall nearly as often as the stone meteorites do. However, they are the ones that people are most likely to pick up when they're in the outdoors. You can stub your toe on an ordinary stone meteorite, and when you look down at the rock, it may look very little different from other rocks in the area, and so you'll pass it by. On the other hand, when you stub your toe on an iron meteorite, you know you've got something unusual. Now, the iron meteorites are extremely dense. They have a density of nearly 8 times that of water. Here is an iron meteorite from the meteorite crater in Arizona. It's quite heavy. When you hold it in here, you can see immediately that there's something unusual about it. The third principal type of meteorite is called the stony iron. Now, this is a meteorite which has too much stone material to be called an iron, and it has too much iron material to be called a stone. So we compromise and call them stony irons. They are the most beautiful of the meteorites, and here is one from Wyoming, Albin, Wyoming. Got a beautiful structure. It's a network, as you can see, a network of nickel iron metal. And there are lots of holes and pores in it, which are filled with the mineral olivine.
Meteorites are hard to find because they look just like rocks, and there are rocks all over the place. Experts, of course, can tell the difference between a meteorite and a meteorong. Now, one of these is a meteorite, and one is a meteorong. This one is the meteorite, an iron meteorite that was found in Arizona. This is the meteorong, a piece of iron magnetite, of course, that comes from the Earth. Well, if you could find a place on the Earth where there shouldn't be any normal rocks, and yet was covered with rocks, you wouldn't have to be an expert on meteorites to know that that's what you had found. Those rocks could only have come from the sky. And there is such a place, Antarctica. Well, to follow up this idea, researchers in the 1970s went to the Antarctic ice pack, and there, strewn across the ice fields, they found hundreds of tons of meteorites.
In the Antarctic or the deserts, the Earth is strewn with meteorites, but other minor members of the solar system, comets, are far less common and at times far more spectacular.
Comets can be found very far back in history, and the reputation of a comet hasn't been particularly good. Comets have been regarded usually as omens of disasters to come, and people have generally then not been particularly happy when a comet appears in the skies. It's not surprising that people would think of a comet this way, for in a sense, a comet breaks the rules. It appears unannounced in the nighttime sky and follows a path unlike those of the other objects in the heavens. Well, the comet then was the traditional herald of disaster, a harbinger of war, famine, and destruction. There was even a medieval prayer that asked for protection from the fury of the comet and the Norsemen. Well, comets have also been associated with great things, great events, great people, and in particular with kings, especially the deaths of kings. In Julius Caesar, by William Shakespeare, of course, there's the quotation that when beggars die, no comets are seen, but the heavens blaze forth themselves with the death of princes. And in fact, Julius Caesar was assassinated on the Ides of March in 44 BC, and after his death, a comet was seen in the sky and was thought by many people to be the comet, the vehicle, in fact, that carried the soul of Caesar up to the realm of the immortals. These are very gloomy ideas about comets, but they're not always the ideas people have had. There have been a few bright spots, too. In fact, a great comet was seen in France in 1811, and that was a vintage year for French wines. And so it was thought perhaps the comet helped those wines a little bit by ripening the grapes just properly, and of course helping the wine to grow and produce that fine vintage that was so characteristic of the year. And in fact, even later, in 1858, when Donati's comet was seen, that too was a vintage year for French wine. And people would treasure those years and those comet wines and use them to mark special occasions and take them out as extremely rare commodities, wines that had been sprinkled, in a sense, by the niceties of the cosmos.
The major observed component of a comet is its huge gaseous head, which is usually thousands of miles in diameter. Streaming out from the head is a long tail, often millions of miles long. The source of the comet's head and tail is material evaporating off the small, well-defined nucleus, which is probably a mass of frozen gases and meteoroidal materials like a dirty iceberg. As the comet approaches the sun, it is heated by sunlight. This heating thaws the frozen gases on the surface of the nucleus, the dirty iceberg, evaporating some of the meteoroidal material. This cloud of evaporated gas and dust reflects sunlight and appears as the diffuse glowing head of the comet. The solar wind and radiation flowing out from the sun gently push the tenuous evaporated cloud away from the nucleus, causing the tail, which streams millions of miles into space, always pointing away from the sun. Depending upon its orbit, a comet may travel around the sun in just a few years, while others may come past only once in thousands or millions of years. The orbit of one of the best-known comets, Comet Halley, carries it around the sun every 76 years. The elliptic path of Halley's comet extends from within the orbit of Venus to a point beyond the orbit of Neptune, where it was in 1948. At that time, the comet was just a nucleus of solidified frozen gases and meteoroidal particles starting to again fall back toward the sun. In 1970, it crossed the orbit of Neptune. By 1980, it crossed the orbit of Uranus as its speed increased. In 1983, while still beyond the orbit of Saturn, it was photographed for the first time since 1910. As it approaches the sun, the fuzzy head and long tail will form as the nucleus absorbs the sunlight. In late 1985 and 1986, observers on Earth will watch the tail of Halley's comet grow to more than 100 million miles in length. Then, as the comet rounds the sun and moves away tail first, the tail will shrink or be blown away. In the process of developing tails and losing them, comets release swarms of meteoroidal materials that follow along the same orbits. In time, a swarm will lag behind or move ahead of the parent comet and gradually spread out around the full orbit. It's these swarms of small particles which are believed to produce the meteor showers which we see when the Earth crosses the orbit of the comet. In fact, it's thought that nearly all meteors, flashes of light in the sky, result from the Earth running into the grain-sized debris of comets, whereas meteorites, rocks that survive to land on Earth, have their origins in the minor planets. There are about 600 comets for which we know the orbital properties. Most of these are long-period comets, taking thousands or even millions of years to revolve around the sun on giant elongated orbits which stretch thousands of astronomical units out into the depths of interstellar space. In 1950, a Dutch astronomer, Jan Oort, suggested that these comets come from a reservoir of cometary material, a cloud of material which surrounds the sun at a distance of about 50,000 astronomical units, or about a sixth of the distance to the nearest star. Nearby passing stars occasionally perturb this Oort cloud, causing some of the dirty icebergs to begin the long journey falling in toward the sun. While there is no direct observational evidence for the existence of this cloud of comet material, the theory is accepted by most astronomers as the best one proposed for the origin of these mysterious interplanetary travelers.
The most popular theory, that's not to say the correct theory, is that comets formed with the solar nebula about 4 billion years ago. As the major planets formed, Jupiter, Uranus, Saturn, Neptune, perhaps some portion of these pre-planetary nebula are formed into a comet belt that was out around the region of Neptune. And now as these comets formed, coalesced, together with the major planets, the major planets and comets are very similar in their chemistry. And so this is one of the major clues that suggest that comets were in fact formed with the major planets.
Dr. Thomas Van Flandern also thinks that the comets formed within the solar system, but at a more recent epoch.
I think most of the data that we have on the orbits of comets can be explained by the hypothesis that they originated in the breakup of a planet somewhere in the belt of minor planets at an astronomically recent epoch in the solar system history. For example, we can understand how it is that the new comets, the comets coming into the solar system for the first time, all seem to be coming in on orbits with periods of 5 million years. If the breakup event occurred 5 million years ago, then all of the objects that were thrown out with periods of 1 million years would have come back in the past. Those with orbits with periods of 6 million years won't be back until sometime in the future. Only those with orbits having periods of exactly 5 million years will be coming back today and will be discovered by us.
The other competing theory is that comets were actually formed outside our planetary system, way outside, in the interstellar region. It turns out that most of them have very elongated cigar-shaped orbits, very elliptical, very high eccentricity orbits. They round the sun, spend a very small amount of time near the sun, and most of their time is spent way out into in space, some, as it turns out, some 50,000 astronomical units from the sun. The problem there is the densities at the beginning of the solar system just don't appear to be high enough to actually form comets. There just wasn't that much material to form them. You don't have that problem if you form them within the solar system, but then you're left with the problem of how do you get the comet population from the solar system to where they now are at some 5,000 or 50,000 astronomical units from the sun. If you form them out there, you've solved that problem, but you've still got the problem of where did the material come from to form them. So you've got a problem with either theory.
About 100 comets have periods from 3 to 200 years, so that their orbits lie essentially within the region of the major planets. When the orbital history of these short period comets is traced back, it is found that they originally had much larger orbits. But on one critical occasion, they passed very close to one of the giant planets, usually Jupiter, and that planet's strong gravitational attraction modified the comet orbit into one of a much shorter period.
With all these minor planets and meteoroids and dirty icebergs floating around the solar system, it's inevitable that good old planet Earth is going to get clobbered once in a while. One of the most recent events occurred in 1908 in Tunguska in Siberia, when there was a tremendous explosion in the atmosphere that leveled trees for over 30 miles distant and was recorded as far away as Europe. We're not sure what that was, but it looks like it was probably the nucleus of a comet, one of those dirty icebergs that came in and exploded in the upper atmosphere. Probably the best known example of a crater, a meteorite crater, occurs in Arizona at the Barringer meteorite crater. That's over a mile in diameter. About 22,000 years ago, a meteorite struck there, the meteorite being about the size of a football field. Recently, some scientists have come up with a very interesting idea that perhaps a meteorite impact did end the poor dinosaurs. About 65 million years ago, a large number of the large animals, mammals, on the surface of the Earth suddenly died. And scientists have been wondering what it was that caused that. One school of thought has it that if a large meteorite impacted on the land, on the Earth, then the explosion from that impact would throw so much dust up into the atmosphere that that dust would block the solar radiation. The temperature on the surface of the Earth would go down several degrees, a lot of the plant life would die, and the large animals would starve to death. On the other hand, another school of thought says that if in the ocean, which is probably a more likely event, then the energy would warm the oceans and thereby warm the atmosphere, and this would also cause the plant life to die due to this change in the temperature. Of course, we don't know for sure if this event occurred, but it's an interesting possibility to a question that's been puzzling science for a long, long time.